221?
Yeah.
Is it okay if I'm here? I'm on the wait list, and I'm just hoping that somebody drops out.
I think I emailed you. Did you get my email?
When did you do it?
Monday at least. Because are you Trinity?
Yeah.
Yeah, so I tried to email you, and the only issue is can you be in the Friday lab section? It's the only one available, so it's like
available?
Yeah.
Yeah, I can be in the Friday lab.
Okay, then I can move you off the wait list, yeah, because I just emailed you to ask you that. But I guess Jenzivar's not working or something.
Oh, okay.
So much for the function of emailing students.
Okay, so I'm good for all of these except one of these are being moved to Friday.
Yeah, so the Thursday lab needs to be moved to Friday, and it'll be from 1 to 4. So it's like a little bit earlier because the lab's at 1:30.
Oh, okay.
Friday will be at 1.
All right, perfect. Thank you.
Did y'all get any notification that we changed rooms or?
Some people's schedules have them in the wrong room, like some people put them in 312. I'm not sure.
Yeah.
I've been in the wrong room a couple times because they changed the rooms that day on my schedule.
Yeah, because I feel like we're missing a lot. We're supposed to have 60 people in here. I think we have a lot, but not 60. So it was originally scheduled for 312, right, this class, or? Wait, 312 or?
The lab is 312.
Yeah, the lab's 312. Maybe people are coming. 320.
My lab says 1:30.
Yeah, that's correct.
312.
counted about 33 of you or so, so I've sent a search party. All right, let's do some housekeeping. So we're probably missing your class, so I'm hoping that they'll show up. Sweet, so we found the class. You got sent for the search party. You made it. Make sure you grab handouts on the back. All right, I was just letting kind of people settle in. So sorry about the confusion. Obviously, we had to have a last-minute room change since I am trying to accommodate everybody. So let's start with the housekeeping business then. So my name's Marissa Shepard. Email is the best form of communication. Although I will admit with the new Blackboard Ultra, it has that giant message tab, so maybe it won't go into the darkness like before. But email's still preferred. You know, I have my phone on me so I can see it immediately and respond. And office hours, we'll talk about this some more, but basically I just want to be available as much as possible before, after class, by appointment, you know, before, after, or during any lab section. So I'm trying to be available for y'all. And so again, we have 60 people in here, and so we have a slight problem. And so my Thursday lab has been oversold here. So Thursday lab, last time I looked at it, it had about 35 students. And the max capacity, though, on the lab is 24. So I need a large group that maybe can move to the Friday lab. So the Friday lab has plenty of space. And so again, this was all, it took a long time to try to get this to happen, and I apologize because then it makes registration a mess. So they added the Friday lab at the last minute. So it's wide open. There's only 2 people in there, so please join this lab. And if you don't volunteer, then we're going to have to start, you know, some forcible methods, which I don't want to do, because I know some people like probably physically can't with your schedule. And if like that's you, maybe you want to shoot me an email and be like, I really can't move. But I would really love it if I could just get, you know, like 11, 12 volunteers to just move. You know, you can make a group of it so you can stay with all your friends. And we can figure this out. You can talk to me after class. So that's going to be on Thursday. So my Tuesday lab is fine, and last I checked, it was full at 24, so that means that can't move in and out, like I said, unless people want to start playing the shuffle game, but plenty of flexibility to move to the Friday lab if you want to go Tuesday to Friday, and then you could shuffle. But yeah, as it stands, only Friday is open. Questions on that so far?
Just so I can scroll to write down your full email.
Oh, sorry.
Okay. Oh, okay, that's really simple.
All right. I guess we'll attempt to call roll now. We'll see how that goes. So I only call roll on the first day to see who's here, and then you can, of course, let me know if I butcher your name or you go by something alternative. All right, Haley Adams. And, you know, give me time to learn your names since there are, again, 60 of you and only one of me. Riley Arnold, okay. Link Baldwin. Oh, walking in. Oh, no, it's okay. I know there was a room change. Nathan B. James Berenger. I think I know James. I don't see him. James. Okay. Robert Berry. Thank you. Lucas Burks. Jonathan C. Thanks. Autumn. Catherine Carney. Thanks. Daniel. With a C? Okay, just checking. Caleb D. James D. Davenport. Oh. Alex D. Brian. Brian D. What's your name? Yeah. Last name? Okay. Hadn't gotten there, but. Oh, I just hadn't missed you, but I'll mark you. We're going through rule. I don't want to miss people. Are you Brian, by any chance? Oh, okay. We'll keep going. We can't find Brian. Jillian. Here. Thank you. Crystal. See you. Madeline F. Preston G. Amy. Here. Jordake.
You can call me Jordy.
Jordy. Kendra. Justin.
Cameron?
Yeah. Caleb H. Holly H. Alyssa H. Ariel. Elijah. Ruby. Oh, Ruby H. So, Bang.
Here. I go with Bonnie.
Bonnie. Ruby J. So that must be you. Campbell.
Here.
Betas, we got you. Kimberly. Avery. You go by Autumn, though? Sorry. Autumn. Reagan. M.
Here.
Alexa Ortiz. Emily Ortiz. Diamond. Elias. Alexander R. Alexander Ragsdale. Okay. Salvador. Right here. Ethan R. Hunter. Or. Sandlin. Emma. Keenan. Christopher. Is that your name, Christopher? Or?
The little Christopher?
Yeah.
Yeah.
Is it? What do you go by? Little Christopher or Christopher?
Anything is fine.
Okay. And then Hunter Tidwell, we got you. Okay, and then Caden, Jeffrey T. Elian.
Here.
Naomi. Sky, I saw you walk in somewhere. Daniel. Nathan Watkins.
Here.
Brandon Wilson. Lexi W. Christy. And Trinity, where did you go? And then Grace. Is Grace here? Okay. And then let's see. I know people walked in. Did Brian ever walk in? No. James walk in? There you are. I saw you. All right. So no Brian. And no Alexander, right? And then was there anybody that wasn't called? Or anybody trying to get in? What's your name?
Jeremy, Jeremy, Garland, Garland.
And you're trying to be in Chem 221? Okay, talk to me after class because I don't have you on the list, but we can squeeze you in as long as you're fine with the Friday lab section. Anybody else trying to take the class, get in the class, in the right spot? All right, let's keep marching on. And so again, we're here, Chem 221. So let's kind of go through the syllabus and how the course works. And so the idea is I'll hand out everything on paper. I can't say I'm the biggest fan of the new Blackboard, only because I feel like it's hard to see now, but that's just me. So under content, things that you want to find. So note that I do stream my lectures, or streaming live to YouTube, and so you can find that lecture link there. And then if you can't make it to lecture, you can obviously watch at home. I just ask, please say hi in the chat so at least know you're live and you can participate. I watch the chat on there. And otherwise, you can watch it asynchronously, so a lot of people have found that pretty helpful to obviously rewatch the lectures. And then I believe there's some textbook chapters here. Hopefully this is the correct book. Where's the book? So this is obviously the solution manual, but this is the book. So it's Macquarie. I think officially the 4th edition, but I don't know if this is starting to get old. So whatever edition is cheap now, just buy it, really. You just need a reference textbook. Macquarie's a good book since it's rigorous for the math. Less relevant in first quarter, but will be very relevant second and third. Otherwise, have you all heard of OpenStax? Yeah, so some people have. If you haven't, check it out. They do have a full chemistry book on there, so they have a lot of subjects. And so I would recommend the Chemistry Atoms First book, but again, once we talk about the equilibrium stuff in second and third quarter, it's a little lacking on the math, so that's why I don't completely recommend this textbook. That's why we stick to Macquarie. It's pretty detailed and goes into, again, a lot more detail with the math behind it, so I like that better. But, use this, maybe a supplemental resource if you want to check out another chemistry textbook. And there's also a free OChem book here, too. So for those of you thinking about OChem in the future, that would also be a good resource. All right, so then, again, idea, you pick up everything back there. And so I have our weeks laid out. I think this lab is probably wrong. And so I want to just talk about the labs a little bit because it's different than how I've done it in the past, just slightly. And so for our labs, once you do your kind of final, or once you turn it in, I'll say. So once you turn it in, you will have to write an abstract. So that's the new addition that I haven't required in the past. I think I did during COVID and kind of gone back and forth. And really, we feel strongly that students need to work on their writing skills and being able to write, especially scientifically. And we will be building up to a research paper at the end of third quarter, so I've added that back in. So I believe the version online, and I'll fix that, it's an older version that doesn't say to write the abstract. But that's why I'm handing you the paper copy of the lab in back. So make sure you grab the paper copy. And so I'll probably say that, like, grab paper copies of everything. So I prefer paper for my sanity. You can turn it into Blackboard, but I probably prefer paper. It's also easier for me to, like, write feedback and, write stuff. And so back there, I put everything you need for the week. And so the syllabus kind of outlines that. So let me look at the syllabus here. So under concourse, and I apologize, I don't print it out, too much paper. And our schedule's pretty repetitive, so you'll get the flow of it. And so we have to start lab week 1 to fit it in with the Thanksgiving schedule. And so we'll start lab, today for those of you who are in lab. And then, we're covering chapters 1 and 2. And so I'm handing you your homework for 1 and 2. And then the quiz will take place next week over our previous material. So this week, that means that we'll have a welcome quiz on Thursday. So nothing that you need to study for. So just our welcome quiz, why are you taking this class? And then so every subsequent week, though, we'll have our quiz over the previous week's content. So pretty self-explanatory. Oh, question?
So I noticed on the Blackboard there are 3 different sort of class sections. There's like a lab and recitation.
Yes, so I only use the lecture shell. I do not want people going in lab recitation. I can barely keep track of the stuff in one shell, so I'm trying to keep it there.
There's also an assignment that said it was due on the 25th. That wasn't there.
Yeah, so please don't tell me that you have an F in the class or like, oh, I didn't turn in stuff. That everybody has an F and your grade will be inaccurate until like the very end. And yeah, I won't go into the rant of to why that is, but you can take that as an opportunity to practice your math skills and you can calculate your own grade yourself. What you do need to get in the Blackboard are the reading questions. So that is the only tricky thing about this class is there are reading questions. These due dates should be accurate. I probably haven't updated the other reading quizzes, hence why you're getting yelled at for missing assignments or who knows what artifacts. So the reading quizzes. And so people forget about those. So I'll highlight that. So we have reading quizzes in Blackboard. So that's just extra reading over the content, the chapter material.
I have a quick question, ma'am.
Oh, hang on.
So,
One
sure.
question.
Go ahead.
Yes. Yeah, you first.
Are we gonna be able to see these notes online?
Yes. So the notes online, so to answer your question right away, I have the live chapter 1 notebook going right now. And so if you click on it, it's updating as we speak with all those notes. So you can see that, follow along. All right, what was your question?
It was just going to be over the reading quizzes. So is that is content coming from the textbook?
Yeah, so that'll be from your textbook. You kind of read through the chapter, may have some history stuff. I don't care if you, kind of flip through your book while doing the quiz. Like, that's fine. It's just kind of extra content so you really dive into it more and kind of extra.
So is the reading quizzes, is it just self-paced or is it gonna flow with what we're learning in class?
I mean, it corresponds with the chapter, if that's what you mean, but I may not talk about it. It's going to have some little history trivia that I may not necessarily cover. So that's why it's over the reading. Yeah.
I noticed with a lot of classes, all the work will be done one day in a week. Is that going to be the case for this class, or is it going to be more kind of individual for each assignment?
So let's talk about due dates. Those of you who know me know that I'm very soft and flexible with due dates. I try to pace things out. So again, where most assignments are due on the Thursday, that's kind of just how it is. I say, maybe do your labs a week after lab, right? So if you have the Tuesday lab, it's due next Tuesday, ideally. If you have the Friday lab, right, obviously you have a few more days. That being said, I don't care if you need to take another day or two to finish up. Just communicate that with me and then get help, right? Because that's where students get in trouble is you start putting stuff off, and then, you're several weeks behind and you just physically can't catch up. And I get it. Stuff happens, right? I don't want to penalize people. I've been that college student that has been sick, and, you get behind. So I want to be flexible. That being said, right, there's also 60 of you, so you kind of, got to keep up pace because I realistically can't grade everything kind of the last week. So does that kind of make sense with due dates? So I'm trying not to punish people, and I understand, like, if you have another class and everything is also due on Thursday, if you need to push mine off a day, but don't let it build up. All right, so all the other handouts should be here. So the homeworks are here, but like I said, I'm trying to hand out physical copies for y'all. But just don't forget about these reading quizzes. Yeah.
And those reading quizzes are just on Blackboard.
Yeah, so there's no paper copy. I haven't thought about paper copy. No one's like asked for paper copy accommodations. So.
For those reading quizzes with the OpenStax textbook, you good enough to follow along with it?
No, that's where you would need the book. Yeah, or else, you may not do as well. So yeah, that's the only thing is those reading questions are tied to the textbook. But if you need help with the textbook, you can always email me. We could try to find you a loaner copy somewhere or something. Yeah.
Where do you think getting the textbook would be best at?
What are your experiences with the bookstore this year? Because they should be, yeah, so you can hold it up. So did you get yours at the RCC bookstore?
Yeah.
Yeah, so RCC should have it, but, again, you're more than welcome to just Amazon, General, Chemistry, Macquarie. And this is brown-looking book. And then, so whatever you can find, it's used apparently for $35, so that's not too bad.
I found it online for half price on Vital Source.
Nice. So Vital Source, right? So you guys can also talk to each other, like source it out. So y'all probably know better how to buy textbooks than me. I get handed textbooks now. All right. And so blah, 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 back to the syllabus. So we kind of continue in this fashion every week. So we do chapters 1 and 2 this week. So we'll try to squeeze that in, continuing 2 to 3 next week. And then just note, right, week 5, we have our exam. So we'll do a review on Tuesday, exam on that Thursday, then lab, blah, blah, blah. And then where's Thanksgiving? So Thanksgiving is week 9, so no lab that week. Thanksgiving holiday, and that essentially just brings us to the end there. So pretty consistent schedule, yeah.
Is that going to be on the notes?
So this should already be there, so you could see that. So this is just the concourse link, sorry. Yeah, so it's just, I should have renamed it syllabus, but it's called concourse. It's like the tool, but yeah, that's the syllabus there, so you can see it. Other questions, logistical things? Yeah.
Are we meeting here permanently?
Yeah. So we had to move to the large room to accommodate everybody. So this is the only room that works.
For the lab abstract, do you have like an example or a guideline or page example?
There's like on the lab handout itself, it kind of gives you an outline, but yeah, I'll have to come up with probably an example. So I'll put that on my list to provide an example for y'all.
Okay, thank you.
Would you be able to, off the top of your head, just recommend an example that we could maybe source?
No, sorry. I don't have an article, unfortunately. Yes.
I wanted to know if we were actually gonna read any, like, chemistry research papers.
So that is kind of the idea. We're going to dip our toe in. So with every lab, there's a research paper correlated with that you'll be writing the abstract over. I tended to pick those CHEM Ed articles just because it's like a little friendlier. Like it's the Journal of Chemical Education. So not as technical, like good way to kind of dip your toe into paper reading. But yeah, that's the kind of the point of the course, right? We want to start getting familiar with the literature. And eventually, we're building up to our research paper in the third quarter, which is going to be about whatever topic you choose. So then you can, dive into the literature all you want. All right, so let's go back over here. All right, I think we're ready to start diving in. Although most importantly, I will say this one more time, is I want you to succeed. So again, there are 60 plus of you, but I tend to be your best did I misspell succeed? Well, no, I didn't. It just looks weird when you put it in all caps. I can't spell very well, so you can always yell at me for spelling. But right, I want you to succeed. So that means, right, it's on you though, to some extent, to come find me, right? Especially when there's so many of you, it's harder for me to kind of keep track and notice like, oh, this person, isn't doing that well. But that's why, right, come talk to me. Come find me after class. That's why I'm saying, I'm available before class, after class. During lab, you can hunt me down. I'm here on campus. I also teach Chem 104, Monday, Wednesdays. You can hunt me down there. I teach lab from like 9 to 12. That's a good time to kind of hunt me down, Monday, Wednesday. I'll say that, right? Monday, Wednesday, I'm teaching like Chem 104 lab from 9 to noon. So you can hunt me down, and I'm in 312. So basically, if I'm not in my office, I'm probably in 312 unless I'm obviously down here with you guys. So, right, hunt me down, find me, email me, whatever, send me screenshots, ask me questions all the time, right? I am your best source of help. The other,
Are you sure it's not 9 p.m. to 12 a.m.?
that would be painful. But, right, so hunt me down all the time. That is the biggest thing. Yeah, something that drives me a little nuts, this happened with my Chem 104 students, and I'm going to tell it to you guys, right? Is after class, they're all freaking out because there's math, and then they're like, where's the tutor? It's like, I'm your tutor. I'm your best resource. Come to me, ask me for help, right? Yes, we have the tutoring center, right? But chemistry is a difficult subject. That's why you have me here. That's why you go to community college, to have this small ratio. Like, I never understand why students are afraid to ask me. Like, that's literally my job, is to teach you and answer all your questions, right?
Do you do office hours through Zoom?
Yeah, we could do office hours through Zoom. Yeah, so I'm flexible, right? Whatever you need me to do, nights, weekends, whatever. I'm trying to be there for you, so there's no excuses. Tutoring center is not that available. All right, so let's get into it. So what is chemistry? What do we think about chemistry? What are our interests, our majors? Why are we in this class? Let's hear some thoughts. Yeah.
Prerequisite for physical therapy.
So physical therapy. So I'll put it over here with medicine, right? So physical therapy. Yeah.
Paleontology?
Paleontology. I haven't heard that one in forever. So I'll put that right. So geology, that always goes into half-life and dating, radiation. Let's see. What's pink hair? Riley.
Podiatry.
Podiatry. So that's like foot doctor, right?
Hell yeah.
Yes. So nice, right? So all that. So more medicine. Autumn.
I need to learn go into material science for civil engineering.
So material science, right? So knowing all our properties, again, knowing our periodic table, very good. Trying to think of your name. Tell me your name.
Link.
Link, okay.
Physics.
Physics. What are you going to do with physics?
Astrophysics.
Astrophysics. So that's a good one. So astrophysics, and right, we'll get into some of that. How do you identify elements by their, by spectroscopy and all that good thing? Let's see. Let's do you in the front. Jonathan.
Genetic engineering.
Oh, genetic engineering. So let's see, where can I put that? So yeah, that's good. Got to know all our properties of science to apply it to biology. Yeah. What was your name again?
Preston, I try Skylar.
Skylar. Oh, I should write. What's your last name again?
Garden.
Okay. And then what do you?
Aerospace engineering.
Oh, aerospace. That's a good one, right? There's a. Are you interested in the materials side of it or more the engineering side of it? Yeah, obviously, right. Boeing's been in the news a lot for negative things, but yeah, perfect time to get into the industry, revitalize it. Let's see.
Nuclear engineering.
Yeah, nuclear engineering, right? A lot of energy. That's always good. Yeah.
Forensic pathology.
Ooh, forensics. So a little bit of mass spectrometry in there and identifying. Yeah.
Environmental science with natural resources.
Nice. What are you going to do with that?
I'm going to be doing grad school for sustainability with medicinal plants.
That's awesome. So, right, that goes into plants and, right, extracting. So there's a whole, that can lead into natural product synthesis that oak chemists do. Yeah, in the back. Vet. So it goes into medicine, right? Again, you got to know all the fundamentals. Excellent. So this looks great. I mean, anybody else want to add anything? Very diverse interests here, which is awesome. And of course, I mean, chemists are biased. They obviously made this graph and put themselves at the center. But I like to think, right, chemistry is pretty important. You have all our atoms here, so obviously we have our periodic table with all our elements. And then how we can combine them obviously dictates all these properties and, you know, however you want to apply them. Any chemistry majors in here? I can hear a lot of chemists. Yeah. And so chemists, I always say chemists end up in big ag. So there's lots of money in big ag, of course, fertilizers, pesticides, blah, blah, blah. So I have plenty of colleagues that work in big ag, and then obviously medicine, big pharma is another one that chemists go to. Then of course teaching. And right, we could even tie into that law. So sometimes that goes well with the environmental science, but any sort of chemistry, right, goes into law, even patent law. So actually, some of my colleagues are in like patent law now.
What sort of field of chemistry would be involved in like a study of metals and alloys, things like that?
Yeah, I mean, that probably is more like materials. So yeah, that's all like materials. Yeah, just trying to get those ratios and rediscover that, what makes the properties. Yeah, so that's all, because alloys are just mixtures. So yeah, that's all materials. Very important. Excellent. So chemistry is important. Obviously, you're here to take chemistry. And so formally, of course, it's the study of matter, and obviously matter is anything that has mass and takes up space, and could be, right, gases, liquids, solids, and we'll just focus on our basic states. And then, of course, we'll be learning chemical changes, so obviously there's a rearrangement of atoms, which I think you all understand, but oh, and then please ask questions. That's the other thing, is ask questions, ask questions, ask questions, right? There's no stupid questions. Some people could have never seen chemistry before and you're taking this class. And so, right, it's supposed to be designed at that level, so just ask questions. And so, right, it gives an example. So, of course, you might be aware that this is a combustion reaction. And we don't have to get into all the terms now. Like, I might be throwing out terms you're not familiar with, but again, we'll get there, ask questions. And so, right, combustion, you think of burning. So obviously if something burns, then it's changed irreversibly. And then in a physical change, of course, we know that matter does not lose its identity. And we can always think of water, since I think we've all seen it in all three states of matter, so solid, liquid, gas. And so let's get into this some more. And, you know, your textbook paints this like really rosy picture of the scientific method. And so I want to talk about that a little bit, especially because y'all are eager to read some papers. And so, right, it kind of has this scientific method. And, you know, we can go through the scientific method, probably what you're used to. So what's a scientific method? What are the steps to it? And again, this is a really cherry picture. Yeah, so some sort of observation, hypothesis. All right, so you see something, and then you make a question, right? And then so from there, what happens after your hypothesis? Yeah.
Do experiments and operations. Make sure.
Yeah, so then, right, you test it, you experiment, right? We verify or disprove our hypothesis. And, right, it kind of says that here, that, oh, we kind of, you know, just go around, you perform experiments, yada, yada, yada. And then beautiful, right, we have contributed to our body of knowledge. And so something about maybe design, repeat first, and then, right, publish, share, yay, it's all happy. And so, right, then it again has this very oversimplification where, oh, now we publish it, right, we're contributing to the body of knowledge. And we'll get into this, so we need to distinguish between a law and a theory. But before we get into laws and theories, I just want to take a step back, because again, right, your textbook kind of does this oversimplification.
So in physics, a scientific discovery is defined by 5 standard deviations from what's otherwise observed. Is there like a standard chemistry that's within like standard deviations?
For like a new
discovery.
I mean, it's just like a completely different criteria, and like it would depend on your field of study. So like usually with chemistry, the idea is to make a new molecule, and so that's like, right, the first step is make a new molecule.
It's a whole different like realm of
Yeah, and so every like field is going to have their own standards, right? So then once you make that molecule, you can't just make a molecule. It has to do something cool too and have a story, so that's all research. All right, so then let's get into kind of when science goes wrong. And I like talking about this paper, you know, not to cast complete doubt in science, but it's to point out that, you know, scientists obviously have their own motives, like they want to get grants, they want to graduate, they want to publish. And, right, we just mentioned that, well, we can't just make a molecule, right? It's got to do something. So there's a lot of pressure in there. And so I like showing this one because it was very egregious. And this was back in 2013. And, you know, it just goes to show that things can slip by, right? Because it's supposed to be a reviewer process, right? This paper goes out typically to 3 reviewers. They all say, yes, no, looks great. And so now it's been retracted. So this is just a blog about it. And so this one kind of shows zoomed up in detail. And you can probably tell, you know, you don't have to be experts in this field of nanotechnology to probably notice that that looks a little funny. So they obviously photoshopped it. And so now you can look at the paper. So again, the paper's been retracted. So they did, you know, eventually people were reading it and noticed like this looks fake. But this is what the, again, original paper kind of had in there. And so you can kind of see the photoshopping. And so, I mean, I think that's pretty egregious, and I think it's pretty egregious that it slipped by reviewers that are, again, supposed to look at that and make sure that things look sound. And so that's, not to get too far down the rabbit hole, but that's the other thing about like any reviewer is they do not like replicate the experiments, right? That's just not really feasible. So all they do is kind of review it and then send it back either for corrections, more data, or, you know, they say, hey, it's okay to publish. So it's a little crazy to me that, you know, again, something so egregious that was Photoshop, fake data, was published. And so, right, that being said, right, there's probably tons of other papers out there with errors. That's not something crazy, either intentional, unintentional, and that's just the reality of it, right? You have to be aware of it, though, so you know what you're getting into, right? So every paper you read, you should read other papers, see if those papers kind of support it. And so that goes back to kind of this. So yes, eventually, right, science, I would say, is kind of self-correcting, but on what time scale, right? So you could be going in the wrong direction for 50, 100 years, and, you know, before a correction is made. And yeah, like even, I'll give one example. Recently, there was an error found in computational chemistry, depending on what operating system you're using. So if you're using Linux, it gave you one answer. If you're using Windows, gave you another. This error was propagated for like 30 years before they figured it out. So, you know, things like that happen. It's just reality. It's science. So, all right, so back to defining these terms here. And so, of course, we need to collect data. Again, very kind of field dependent, as we're already kind of determining. And so what's qualitative data? What does that mean?
Data that isn't expressed in numbers, so anything that is observed and written about but isn't quantified or put into strict mathematical terms.
Excellent. So I like that definition. So again, not expressed in numbers was a good way. So anything that you observe. So what could fall under that? So what would not be numerical?
Color something or the shape.
So color, shape, what else? What did you say? So size, although size is probably, could be like more number, right, if you get quantitative. Behaviors, maybe? Yeah, behaviors, that's a good one. So now thinking about more biology science, right, observing monkeys or whatever groups.
I'm going to say relationship, one to another.
I'll put that under behaviors.
Emotion.
So emotion.
More like when you mentioned plant, it just made me think of how one plant can exist next to another. Yeah. The relation to each other, like how they will react.
Oh, yeah, just like symbiotic relationships and going into all that, yeah, details. Other things, kind of chemistry related, yeah, in the back.
Like maybe taste or smell?
Yeah, that's a good one. So taste, smell, those are more, right, chemistry relevant. Maybe not always taste, but, you know, sometimes taste. Well, again, we won't go there, maybe.
Texture?
Texture's a good one. I think we've got it. Any others?
Quality.
What was the last one? Sorry.
Quality. It was qualitative.
Oh, quality. Yeah, I mean, I guess you could give it a grade, right? Like trading cards. Get those rated. Okay, that looks pretty good. So what about quantitative data? So what is that? Numbers. So yeah, easy definition now. So anything involving numbers. And so what could this be? Examples or? So any sort of statistics data that could be, I'm thinking back to like a mean population or something. Growth rate. So. Yeah, temperature, let's do some easy ones. Y'all are like all ecologists in this room or something. Yeah. Yeah, I would say so. So stoichiometry, because that would be like amount. All right, so that's just our fancy word for amount of stuff. Yeah. Yeah, mass is a good one, right? We can measure that in kilograms, grams, or milligrams, right? Those are the typical ones in chemistry, but obviously not limited to. Other thoughts, I think we'll go back to the size one, right? So I'll put size, length, density we'll put in there, right? Length, width, height. Time. And I'll go back to, right, either time to something or maybe even, again, like half-life data. That's where we see time most relevant. Could also be reaction rates, though, but in this class, we just don't typically address reaction rates until much later in a very specified environment. All right. I think we've got all of them. That's pretty good. And so with that, I'll kind of add like another little caveat to think about. And again, right, this is specific to any kind of research setting and also something that we want to think about, right, as we're in lab, as we do our measurements and kind of do this first chapter. But we always have to think back to, right, how accurate are these measurements? So you're always thinking about that, right, in the back of your mind, right? Is this the correct technique? Is this the correct ruler to measure that? You know, anything like that. Yeah, I mean, you could start getting into all the different specific spectroscopic techniques of chemistry, right? How you actually accomplish these different measurements. All right, let's define these other terms. So what's a hypothesis then? Yeah, so educated, and it's just a guess that, and I'll add the word, right, attempts to offer an explanation.
Does every scientific paper have a hypothesis?
You know, not really. Like, it's kind of funny, right? You say, like, oh, yeah, we got to have this formal hypothesis, but, like, in your paper, you don't really say, like, this is my hypothesis. But instead, and this goes back to, like, what you need in the abstract, is, like, you want to give a brief detail of, like, you know, where the literature stands. So, like, in my field, it's, like, what similar compounds have been made that do, so I was into CO2 activation, because obviously I was going to save the world. All right, so where does it stand with CO2 activation? So, yeah, that sort of thing. So then it starts talking about that. And yeah, maybe you make a prediction. Hey, we're going to make this molecule because it looks kind of similar to these things. And we're going to put these two elements together. And obviously, we're going to make the perfect molecule, right? So yeah, kind of like that. But you're right. There's no like, this is our hypothesis that we're testing necessarily.
I think there'd also be like a lot of accidental discoveries in chemistry as well. So.
Yeah. And, you know, it goes back to you're trying to write a story to sell. Because ultimately, right, you have to turn back around to like NSF and say, hey, I need money for this because I'm saving the world with this cool molecule. Yeah, very competitive. So that's the nature of the beast. So what's a theory? Autumn.
I believe it is some sort of idea or a set of ideas that has been proven enough times to where people can kind of say, this has been shown to happen often. However, we haven't quite gotten the amount of times, right, to say it's like a firm law or truth of chemistry.
That's not true.
No, really?
Yeah. So that's that. All right, I'm glad you made that mistake, though. So that's a good distinction, though, right? So that's kind of the thing. Is it's not that the theory is not a law yet. Is that they're separate. Do you know the distinction? Or?
Wouldn't a theory be more speculative?
Yeah, so it is speculative, but it is backed up by evidence. So we synthesize it to one better answer.
I think a theory is sort of, it's not necessarily a fact because it hasn't been proven, but all of the evidence that's, virtually all the evidence that's discovered points towards the theory being true. So it's not like concretely proven yet.
Exactly. And that's kind of the thing is like it literally cannot be proven completely, right? Like we cannot know.
Same is true for a law, right?
So the law is always true. So that's just it. So the law is more, I would say, like a proven, and it's generally mathematical. Right? Relationship. And so, right, it's kind of like, yeah, so basically for a mathematical relationship, that's just like F equals MA, right? That's always going to happen. F equals MA, right? You can do it a million times. E equals MC squared, and then you can have a relationship, right? You can drop your object a billion times and know when it's going to hit. But then actually explaining what's going on, that's kind of the theory, right? So it goes back, so we can think of like Big Bang Theory, for example, right? So that's a good one. So there's lots of evidence to maybe support a Big Bang. Yeah.
So is a law kind of like a proven conclusion to something, and then the theory is like explaining how that happens?
Yeah. So that could be the case, exactly, right? Where you have this law. So the law is literally just the mathematical relationship. It is always true, right? So it's always saying this is always happening. But then it's not explaining, yeah, the why necessarily. So the theory does attempt to offer an explanation. Oops. Sorry. Let me move this down there. So we'll say that our theory attempts to offer an explanation for a known phenomenon.
I once had a whole argument with a kid in high school about the theorem of gravity because he was insisting that gravity could not be real since it was only a theory, and I couldn't get him to understand what theory meant in science. It was very aggravating.
Yeah, so that's like a good point. Is right, so you have this mathematical relationship, right, relating to bodies. I can't remember the formula right now, but there's something, right, mass times mass over r squared gives you some force relationship between them. So I'm not a physicist, but, sorry?
I happen to have another good distinction that I wrote down yesterday. He separated, the other professor separated it by the difference between hypothesis and theory, the hypothesis being the prediction based on observation, the theory being the conclusion based on experimentation. And then the difference between the law and the theory was every law is based on a theory, but not every theory is a law.
Yeah, I mean, my problem with that definition is we really want to say that the theory has been proven over and over and over and over again by a phenomenon. So again, going back to like Big Bang Theory, right? So we see evidence of an expanding universe. So you could talk to physicists about that, oh, okay, we see that our universe is expanding, so that's why they think, right, we started at one point. And then, right, other phenomenon to, again, support the Big Bang Theory and all those things. So that's where the Big Bang comes from, right? Again, it's just a theory, though, right? Because no one was literally here looking at the Earth or looking at the universe, right, to see it explode if it did indeed explode. So that's kind of the point. And then, like, going back, so like germ theory. Like, germ theory is still a theory, right? So we're pretty sure that, yes, there's these little things called viruses and bacteria, and they make us sick. And we've seen this evidence over and over again, right? We've isolated cultures, but it is still just a theory. Autumn.
Do all laws have to be mathematical,
I can't think of a law that isn't mathematical, because that's generally the point, is like, there's an outcome.
Mhm.
You know, that being said, I could, probably not thinking of something, but. What about what?
No,
The
that's-
First Amendment? There's always freedom of speech in a chemistry classroom. That's all I have to say. But, so does that kind of make sense? So, right, the hypothesis is just kind of one instance, but then the theory is, again, like, right, decades and decades of research coming together to form this theory, right? So it's a very long process. It's not just the conclusion after one experiment, right? That would not be enough to do a theory. You have to keep combining every experiment over, again, centuries, really. Yeah, it's kind of interesting, like, yeah, again, right, you had, we'll go back to gravity and how you're trying to explain to your friend, and even probably back in the day how they were trying to understand it. It's like, there was this, again, mathematical relationship between two celestial bodies, and like, back in the day, they could understand that mathematically, but then the theory of trying to explain it, they couldn't. And so they actually invoke God in their explanation of like, you know, that it's God holding us together and all these gravitational forces, so it's kind of interesting. So that's, again, you know, the difference between the law and the theory. So. Okay, so typically how I do the lectures, since it's a 2-hour chunk time, is I give y'all a little 10-minute break. So I think that's a good place to take a little break. And so let's reconvene at 12:05 or so, and we'll continue on with our metric system next. Morning.
So, I can't remember the other professor's name, but I was going out to Grants Pass.
Oh, Sakar?
Yep. And he reached out to you yesterday concerning me and said that you would accommodate.
Yeah, I said as long as you can do Friday, then, so are you not on my roster then?
I'm not, and I still need to do
Oh,
the-
so you're Jeremy Garland. Okay, sorry.
Yeah,
Just
all
putting
good.
2 and 2 together
All
right
good.
now.
Yeah, so I will email you again today because I have to go into, and my name is spelled Jeremy. That way when you see it come up.
Okay.
I'm not giving you crap for your spelling. No, but I have to go over into the lab and the recitation in this class, so you'll see all 3 of those.
Yeah, that's fine. Yeah, and it shouldn't be a problem, like I said, if you sign up for the Friday lab.
Thanks for your help.
Yeah.
I do appreciate you doing that. 'Cause
Yeah,
that's a
of
long
course.
way.
No.
Yeah, cool. Thank you.
Trying to squeeze everybody.
Hi, I was just wondering, I've never taken chemistry before. Do you think it's a good class for me?
I mean,
Is it like somewhat advanced or?
it depends how you feel. So like the official answer is this class is meant to be taken with somebody with 0 chemistry background. So we are gonna like cover everything, but we do move at a fast pace, and some people in here have taken like Chem 104 with me.
Okay. Yeah, so I'm taking like physics, but nothing to do with chemistry.
Yeah, I mean,
I'm taking it for prereqs to go for like a year or 2 before I go to Oregon State for forestry.
yeah, I mean, I would honestly say that you just like stick with it and do it, and like it will probably be hard in the beginning.
Okay.
Like, you know, there's just no way around it, because like the beginning part of chemistry, I always say is like a new language.
Yeah.
So you're gonna learn all these symbols and formulas and stuff. So if that's your first exposure, you know, it'd be difficult, but I think you should do it.
Okay.
And you know, again, bug me for help all the time.
Okay. I just wanted to thought it was a good class for me.
Yeah,
for, like,
'cause-
my plans. And,
Yeah, because you want to get it if it's prereqs, like, yeah.
Yeah. All right. Thank you.
Do you prefer Marissa or Miss Schumer?
Marissa.
Marissa. What is that tool that you're using on the OneNote that's creating that space?
Oh,
No. You move everything
oh,
down. Saw you do it a couple
insert
times.
space.
Insert space. Okay.
Yeah.
Yeah, I use OneNote. And
Oh,
I
nice.
saw that and I was like, what is that?
Yeah.
The online you have a couple of the PDFs for the chapters, like chapter 1, 2, and 3. I find it a lot easier for myself to go through on OneNote with the chapters in there to like mark it up.
Yeah,
and read
it
and
should,
stuff.
the OneNote should be there.
I did buy the book already. I was wondering if you have the rest of the chapters in PDF format.
Oh, you're talking about
Just
the
so,
book.
like for the rest, yeah, for the books.
I think, because I only have those chapters on there.
I was gonna go through the lengthy process of scanning the book in. I already got like the spine cut off and everything, but if I had the opportunity to get ahead
Yeah,
of it.
I don't think I have like other resources, unfortunately.
Okay, I thought I'd ask. All right. Well, thank you.
Yeah.
Alright, so we're thinking of switching into the Friday lab.
Okay.
He, however, is on today's lab, so he wouldn't
Oh.
apply to, yeah.
I mean, you can. It's not a big deal.
a while ago, like
Oh.
a week or two ago,
Yeah.
about like switching into their lab, but then you said it was full. I
Yeah.
didn't realize that I could carpool with them both days, and the whole problem was gas money. So
Yeah. So do you all? I mean, I don't have a problem.
It would just be us two from the Thursday lab switching in. Just
Yeah, but
be
then.
switching in from the Tuesday.
Yeah, that's fine. Yeah. Okay.
So
Sorry.
would you want us to go into the thing right now to switch our classes?
What's your name?
Amy Gobbin.
Sorry. Friday. Okay, and who else?
Bonnie or Bang.
Bonnie. And then what's your name?
Nathan Watkins.
Okay. Perfect. Can y'all try to fix that on your schedule?
Yeah, do you just want us to go in and then switch into and drop out?
Yeah, so drop one, and then it shouldn't be a problem to add the Friday.
Okay.
Since, like I said, it's wide
Do you
open.
want me to still come to the lab to the Tuesday lab today, or do you just want?
No, I just come to the Friday, because then maybe somebody can sneak in if they need to.
Hi, Holly Hawthorne. I just wanted to give you a heads up. I 100% can't do Fridays because I work and teach on that day.
Okay, so Holly
Yeah.
Hawthorne.
Yeah.
Okay, I will put you.
Thank you. Sorry about that.
No, it's
Cool.
that's what I needed now. Is who absolutely can't switch.
Hi. So I sent an email a couple weeks ago. I'm not sure if you got it because I didn't get a response, but I might have just sent it from the wrong email. I have a doctor's appointment today at 4. So I can be here for like the first half of the lab, but I have to leave early to make it to that. I don't
Yeah.
have any other conflicts with any of the other
That's
labs.
fine. I think
It's
that'll
just
work
today.
for today.
Okay, awesome. Thank you so much.
How do you access Blackboard?
Can you pull up your computer and like go to My Rogue and stuff?
I don't have my computer on me.
Okay.
I didn't know I was supposed to
Talk
bring
to
it
me
or
after. Well, you don't need it, but if you want help, then you have to talk to me and show me, or go to a computer lab at some point.
not. Okay.
Yeah. Do you have lab today by any chance?
Yeah.
Yeah. So then ask me then, and we can get on Blackboard.
Okay.
So yesterday I was looking through all the online documents and looking at what you have written down here.
Yeah. I'm. It's fine.
Are we worrying about that? Or-
No, I guess I should have said no. That I don't grade the pre-labs.
Okay, got it.
I grade them at the end, like with the post-lab. I mean.
Hello. So I'm one of the people that messaged you before term started, and I managed to squeak into Thursday labs. I can't do Fridays, but
Okay.
I might be able to do Tuesdays.
What's your name?
Autumn Caldwell. Yeah, I work Fridays, so I have
Okay.
and there's no way around it. So
Okay.
I have
no
class the
Friday.
other day.
Okay, noted.
Thank you.
Just got a question. About your are we doing lab reports in this class?
So all you'll do is like fill out the lab report, but then add an abstract to it.
Okay.
So yeah, not like a whole formal write-up, but yeah, or at least not yet. I've debated it.
So I just have a question. So I have I play for the soccer team, and we're leaving today at 1. But not to be at the Tabora campus at 1. So I was wondering if it's okay if I leave like 10 minutes early.
Yeah, that's okay. Yeah, and you can always catch the lecture on YouTube.
Thank you.
And then I assume you have lab.
I just saw you have like a little directory outside for RCC. There's like an environmental club that you
I'm in charge of the Earth Club. Yeah, I'm in charge of Earth Club.
When does that happen?
I don't know yet. When do you want it to happen?
Oh, gotcha. I don't know, like Tuesdays, I guess.
Are you Hunter Tidwell, right?
Yes, that's
Okay.
correct.
I will note that I should.
So I want to go into like sustainable energy science and stuff.
Yeah.
Oh, thank you.
Yeah, we'll chat later.
Just a quick question. Am I gonna just put music on one ear really quietly?
Yeah, I mean, as long as nobody else
Yeah, no.
hears.
I
Yeah.
just want to make sure with you before.
Yeah, that's fine.
And then I didn't see the Tuesday lab earlier. Do we have the Tuesday lab still?
Yeah, so there's still
Okay.
Tuesday lab. I just didn't talk about it because it's just that it's fine at 24, so I don't need to like do anything to it.
Got it. And then would it be, what room would it be? Would it be?
312, so it'll still be in 312. Yeah, the labs will always be in 312.
Got it. Thank you.
You mentioned these notes can be found in the Blackboard somewhere.
All right, did we all make it back? All right, so let's keep going. And so, and again, right, ask questions. I know some people may be bored of this and you've already seen it. Some people could be fresh. So just kind of, again, bear with me as we all get on the same page. And so now the next question is, you know, again, we have a lot of diverse interests. We had astronomy, right? A lot of future ecologists that probably want to measure the soil and what's in there. And so how do we deal with this large range? And kind of, let's even get some idea of, well, what ranges are we going to be working with? So thinking back, right, somebody was interested in forensics, so you might have to do some human hair analysis under a microscope, comparing hair samples. And what scale is a human hair on? Any idea? A little too small. Yeah, so micrometers, so about 1 micrometers, or 1 times 10 to the negative 6 meters there. So that's good. What about the size of an atom? And you could give me 2 answers for this, or several answers. What unit? Oh, atto's too small. I think that's negative 18. So pico would be good, or not pico. So pico is negative 12, a little too small. Yeah, nanometers though would be one answer. So we could say on our nanometer scale, 1 times 10 to the negative 9. And then what's another unit though? And I think you were maybe trying to go for it, but I didn't quite remember the name. Any other guesses? The chemistry unit? It's this little symbol. So this is an angstrom. And that's just a special one that chemists like to use. So 1 times 10 to the negative 10. And so I believe a sodium atom is 1.5 angstrom. So it just works out nicely for chemistry, you know, nice numbers. So they like that unit. So you may see that. Let's go big. So we had, again, a bunch of biologists, ecologists, and now we're measuring elephants. So how big are elephants? What scale? So tons, right? So probably, I think that's like 2,000 to 6,000 kilograms roughly. So pretty large. And then if we get into astronomy, so anybody know the distance in light years? Yeah. Yeah, so about 4, I have like 4.35 in my notes. I think that's just a made-up unit. Isn't it like a, yeah. And I think they use the unit improperly. And then that's about a lot of kilometers. So about 40 trillion kilometers there. Or, so million, sorry. Oh, I left off a 0, that's why. 40 trillion, sorry. 1, 2, 3.
Oh, really? Yeah. It's the equivalent of about 3.26 light years.
Good job, Star Wars.
So very large. So then, right, the next question is, well, how do we deal with this? And so we have both our scientific notation. And so, again, pretty basic, but I want to make sure that we're all on the same page. So do we know how to express numbers in scientific notation? So of course, right, we have our negative exponents. And we can see 1, 2, 3, 4, 5. So that's how we got 2 times 10 to the negative fifth there. Obviously, right, small. And then large numbers, positive exponents. So 1, 2, 3, 4, 5, 6. So 2 times 10 to the 6. Yeah.
So something that's always confused me about scientific notation is what happens if you have a measurement that's kind of a floating point with just sort of a ton of, after the decimal. At that point, do you condense it to a certain amount? Is there like a standard for that? Or?
Yes, so we'll get there. We'll answer your question because we'll go back to sig figs and going back to what we said right over here where we're saying, well, how accurate are these measurements? So hold on to that thought. So we'll cover it later. So before we jump into sig figs and how to do the math, I at least want to briefly talk about the metric units. And so you're probably aware that we have our base quantities. So chemistry uses this mole amount. So we'll, again, talk about that as we progress on our chemistry journey. And then you're probably familiar with meters. So that is considered the base unit for length. Then we have grams. So that's our base unit for mass. And then liters. And so these are probably the important ones you want to focus on. And then we don't really do like the prefixes with temperature, but I'll just kind of add under here. Really, chemistry focuses on Kelvin. This is thermodynamically relevant, so we'll revisit that thought later. And then, of course, seconds and bytes, which we just don't really deal with information or a lot of time here, honestly. And so then, of course, you're probably aware of this, that our multiples of 10 are created by adding our prefix to our base. And so I printed out another handout that's in the back. Let me go grab it for a second. And so I use this in my Chem 104 class, but I thought that y'all would probably benefit as well. And this might be something that you fill out kind of on your own time to help you. We can talk about this individually. But basically, I'm trying to make up a little cheat sheet for y'all. And so we can look at kind of your multiplier. And so you can look at your sheet. And so this is, and it's on your sheet here. And I apologize that I don't have a PDF copy. I didn't get a second to move it over to my notes. But the multiple here, this is always right by the base unit. So this multiplier here is by our base unit. And so something that you want to do then is, especially if you're not comfortable with like this math, is you probably want to go through and set up your conversion factors. So I'll probably add this to the notes later. And we can go through a few conversion factors. But all our conversion factor is a relationship. So I want to make that kind of clear, right? So it's just a relationship to do some sort of conversion. So right, think back, well, we have 12 inches in 1 foot. That's a type of conversion, right? We have 100 pennies in $1, right? That's another conversion. So that's all we're saying, is we're just expressing relationships And then this point is just saying, well, we can flip it around too, right? It's still the same relationship. Well, 12 feet, 1 foot is 12 inches, right? $1 is still 100 pennies. We're just kind of writing it in different forms. Again, kind of depending on which way we're converting, which we're getting into. And so again, that's all we mean by our conversion factors. And I am going to kind of push this dimensional analysis method only because it's helpful, especially once you get into stoichiometry and you're doing multiple conversions, back and forth. You don't want to lose your place. And I, understand that there are plenty of other mathematical methods to get to the same answer that I'm doing. Feel free to use those, proportions, blah, blah, and we can always talk individually about other methods here. All right, so I think I'm going to hold my thought on practicing on metric conversion for a second, and let's instead talk about significant figures, and then probably we'll use Thursday to practice what we need to practice, and that'll give you time to kind of work on this. And so now we're going to answer your question, right? Because you said, well, how do we know what to report to? We're going to just keep going on and on and on forever. How do we know? And so this is key. And I think we'll get a taste of this next week in lab, if I remember. Some of it today, because anytime we do measurements, right, we're always wanting to apply these principles. And so it says, right, reporting of significant figures in an answer is dependent on the precision of the measured values in the problem, which is determined by the precision of our laboratory glassware. So that is extremely important, right? It's like we are physically limited. And you're only going to get a small taste of it now, and then if you really want to get into the precision of your measurements, you can go on to college and take analytical chemistry, and you'll be calculating every little error and propagating that error and figure out how really accurately you can determine anything. So that's where that comes from. And so what we're saying too is, like, you're going to go into lab today. You're going to measure out some popcorn. And if we use what we call our regular balances, I'm just saying regular. So our kind of regular balances that you'll see in lab, they only go out to 3 decimal places after. So that means you want to record every value. Every value is important on that scale, right? So you record it down. So these are your significant figures. Even if you had 50.000, right? That's significant. They're all significant. It is saying we measured it out all the way out here with our accuracy of our balance, right? And then going up to the analytical balance, why it's called analytical and costs $2,000 or more, is because it goes out to 1 more decimal place. You really got to pay for that decimal place. And so yeah, again, you would record every value, and maybe even in that case, right, it's 50.0001 or something. So that's the difference, right? So now we're saying more accurate balance can measure more accurately, keep all the sig figs. So that's important, right? You want to report everything that you're recording. Because obviously, right, if you're already losing information in your recorded data in lab, that's going to compromise, right, the integrity of any results. And then, so the next thing to keep in mind, so when we do this, so right, you may get, let's just say, a length, and then we need to convert it. Well, our conversion factors are treated as exact values. So that basically means we ignore them. And that makes sense, right? Because we would only have 1 sig fig for a 1 inch to 2.54 centimeters. So you don't include them in your sig fig kind of calculation. And so now let's go through, well, what are sig figs? How do we determine them in a problem? And so, of course, right, again, anything that you write in lab is significant, and you want to also measure accurately enough to reflect that. And we'll talk about that again in lab as kind of a case-by-case basis. But let's say, so we're doing some problems now, right? We're given data. Well, how do we know what's significant or not? And so kind of our first rule here is all non-zero values are significant. I think that's relatively self-explanatory, right? If it's a number, it counts. So 536 has 3 significant figures. And then the next one is also pretty self-explanatory, and I call this our captive zero rule. And so all that means is when we have a zero between other non-zero numbers, it has to be significant. And so now let's go to our not significant, and I'm going to summarize these two rules here by these show magnitude. So what does that mean? And so let's look at this next rule. So it says leading zeros. Placeholder zeros to the left of a non-zero digit are not significant. So basically, right, all these numbers are showing how small it is. So not showing accuracy, just merely reflecting, how accurate, how small our measurement is. So that's just showing how small, not significant. The other kind of key that helps you determine whether it's significant or not is, can you rewrite it in scientific notation and get rid of it? And so write a clearer way to write this. So we have 1, 2, 3. So we could write 4.3 times 10 to the negative third. And we don't have a unit on here. But now that's clearly showing, okay, I only have 2 sig figs. So that kind of can be useful. And then trailing zeros are also not significant. So again, this is showing how big now. And so maybe, right, again, this could have been a wildly inaccurate scale. You've seen those like weird, crappy industrial ones and trying to just weigh something really quickly. And so we only have, 1 sig fig. So maybe it's 7,000 pounds, again, inaccurate. And so again, that's reflected in our calculations. Yeah.
So I have a question about the trailing zeros here, because anytime you get a measurement from a scientific device, there's a certain degree to which it's actually accurate. So any measurement is most likely going to have a floating number of random digits at the end, because the measurement is only accurate to a certain point. So how do you know how accurate your device is?
Well, usually it indicates. So again, like on a scale, you usually want to record everything. And, if the scale, like I said, if it's a really crappy one, potentially, like it could say like its tolerance or, kind of what they're rated for. So when you go into lab, too, you can look at the graduated cylinders and they say plus, minus, whatever.
How do you figure that out?
Well, somebody had to calibrate that originally, right? So then somebody does calibrations, right? How accurately are these things made? And then obviously the more expensive something is, the more accurate it is. That's number one rule. You want something accurate, you pay money. All right. Does that kind of make sense? Yeah, and and these could feel unrealistic to you, right? Like, well, you probably wouldn't have such an inaccurate scale that you would, have 7,001 sig fig. I get that, right? So we're just kind of going through the theory of that. And then, so this one, again, 0 at the end, so showing not significant. Notice that we do have a captive 0, so that is significant. And so let's go, actually, back to your point for a second. And maybe we're at a situation, so we have 7,000, but let's say it's pounds, and right, plus minus 10 pounds or something with the accuracy. So now we're saying, well, we can say that these first 3 digits are accurate, and I want to show that. And so how you can show that, though, is again by writing it in scientific notation. And so, for example, again, if we write, so 7 times 10 to the third, so that's 1 sig fig, clearly showing that. I could write 7.0 times 10 to the third. Now that's saying that's accurate to 2 sig figs. And then again, let's just pretending that this is, right, the accuracy of whatever crappy industrial scale we're using. Okay, so now, again, I can know it accurately to this 10th place, or no, 10 pounds, so I'll write 7.00, 10 to the third, 3 sig figs. And obviously, right, we can go on and on indicating however much accuracy we needed to with this measurement. Does that kind of make sense, clarifies?
I'm confused about the second example, for zeros to the right after a decimal point. So in the second example, 0.0600.
What, sorry,
Yes, the second example.
oh, here, 0.0600.
Yeah, so so the zeros that are highlighted in red aren't?
They are.
They
So,
are significant. But then the zero before the 6 isn't?
correct.
Leading.
Yeah,
Like
so
after
let's,
the decimal point?
yeah, so let's look at this rule, right? So now you're looking at this rule. So now it's saying zeros to the right after a decimal are significant. So what we're saying is these are zeros that are not showing magnitude, right? And so that's kind of the distinction.
They're not in scientific notation. Is that the same thing?
So you could rewrite it in scientific notation, but you can also tell, right? So you have 50.0. The fact that you bothered to write it after the decimal point must mean that your equipment was accurate enough to measure to that amount. Yeah, so then this is saying that this is all significant. And then, right, this, of course, interior 0 becomes significant. But then the point was, right, this measurement. Well, we have 0.06, so this first 0 is merely showing how small. And then these last two zeros, the fact that, again, you put them after the decimal point, right, is saying, yes, we can measure it this accurately, right? Thinking back to our analytical balance in here, so maybe we did actually measure 0.0600 grams.
So the extra zero there is significant because the equipment used to measure is accurate at that point.
Yeah, and so when you write it down, you're reflecting that accuracy, yes. So then, again, this looks like an analytical balance, you know, your $2,000 analytical balance, you can measure something that accurate. And so generally with the analytical balance, the fluctuation is always in the last digit, so that's where you're going to see, right, your plus minus 0.0001 grams. Yeah.
So if I take that 7,000 and put a point 0, does it have 5 significant figures? Or does it have 2?
So you want to take 7, oops, sorry. So you're saying 7,000 and then put a 0.0, and that would be 1, 2, 3, 4, 5 sig figs, yes.
Yeah, okay.
Yeah, so that is, right, different ways to show different accuracies. It just depends, again, back to your equipment, what you're using, dictates what you're reporting, yeah.
But if it was just like 700 and it didn't have a decimal, it would just be one significant figure?
Correct. Yeah, so in case you didn't hear, the decimal changes how many sig figs. That is important, and we're going to go through a few more examples. So yeah, 700 is just 1 sig fig. You could see something, this would be weird. How many sig figs? 3, yeah. You don't often see that because usually when you start doing weird stuff like that, you want to throw it into scientific notation so it's clear, but you could see that.
Wait, so that decimal point just indicates
That these are significant, yeah.
why?
That's a formality. So now you put a decimal point there, so you're saying that yes, it is accurate to before that decimal point. Yeah.
So you would do, what, scientific notation 700 times 10 to the 0?
Yeah, so it'd be 7.00 times 10 to the 2 would be the best way to write that. So these would be the same thing, right? 3 sig figs.
Yeah.
So yeah, there are multiple ways to kind of express how many sig figs. All right, let's do this practice question. So take a minute or two, kind of go through it silently, and then we'll do fingers for the answer.
So why is I guess maybe I'll ask another question for it. I'm still just a little confused as to why those leading zeros are not, I mean, it shows magnitude, right?
Yeah, I mean, that's just like the rule and also just, you know, how you treat it, right? So the ones that are just showing how small, they're not included, but then anything after, again, is reflecting accuracy. All right, let's try to go through this. So what do we think for 1? Show me, I see lots of 2s, excellent. So 2 sig figs, what about number 2? 3s, 3s, 3s all around, excellent. What about 3? 3 again, so make sure it's just 3, right? So all these are leading. So it's just those 3. And then number 4, excellent, I see a bunch of 2s. And then what about 5? Yeah, 2, excellent. So you did not get tricked. So again, this is one of those weird ones where I don't really like it, right? It looks kind of weird. It's probably better to rewrite it as 1.0 times 10 to the 1, so that's really clear that yes, we have 2 sig figs, and you know, it's not like a period or something. That's totally easy to confuse.
So leading zero is anything that comes before a non-zero value.
Yeah, that basically just shows how small. Yeah, so this, all these zeros, right, they're all just saying how small, and right, same thing with all these after, they're just saying how big.
And then the trailing zero there is actually a trailing zero because it comes after decimal.
Which, yeah, because there's no decimals, yeah. So it's just showing again how big, right? So there's no decimal point.
I mean number 3.
Oh, number 3, so all these.
And then the last zero is not trailing because it's after decimal.
Yeah, so then it is significant. So it's right, it's saying that whatever we were using, whatever value is measured accurately to that amount.
How would you write number 3 in scientific notation?
So let's count 1, 2, 3, 4, 5, 6. So 2.10, right? You want to put that 0 times 10 to the negative 6 there. And so that, again, very clearly shows the 3 sig figs. So anytime you can just get rid of it with your scientific notation, right, you know it's not significant. Questions about this? So we'll keep practicing. Like I said, we'll probably do practice on Thursday. Yeah.
So, number 5, so there's 2 because it is decimal, but if it wasn't a decimal.
Correct, yeah. So, and then, so let me rewrite that. So yeah, just for clarity, just 10(0) is 1 sig fig. And again, right, maybe 1 times 10 to the 1 is a clear way to show the distinction between those. So we'll revisit this, we'll keep talking about this, but I at least want to go through our temperature scales and other properties before we go do math review. And so temperature scale, what do y'all know about Kelvin? Why do I say Kelvin is thermodynamically relevant? Yeah.
Because isn't it based on like the speed that the temperature is just how much energy molecules have, like how fast they're moving. And so like 0 Kelvin would be if the like a molecule was or an atom was like completely still, which I guess absolutely impossible.
Yes, excellent. So perfect definition. So just like he said, right, temperature is related to motion. So absolute 0, complete absence of motion. So again, right, we have to think about what that means. And we're talking about, right, your electrons would stop moving. And so that's always something to think about, right? You have a solid object. It looks solid, but it's not solid, right? It's vibrating. Your atoms and electrons are moving around. So there's still movement.
Is there an opposite of absolute zero?
Not one defined. I mean, we could get into like, well, there's technically critical points of substances, you know, where it's all the states of matter, but I wouldn't say that that's necessarily an equivalent. Yeah, I should have posted an article. I didn't think about this. I'll probably post it later. But obviously, this is an area of research. So people are trying to get down to as close as they can to absolute 0 and I was trying to figure out how far they are. I'll have to look. Yeah, because I remember a couple of years ago, I think MIT had gotten down to like 0.4 Kelvin or something like really, really crazy. But I'm not sure exactly where the research stands on that, so I'll try to post an article.
When you get down to temperatures that low, atoms start to melt together into a thin state of matter called a photosynthetic density. People are using those in airplanes and stuff to like figure out how far they're going and whatnot.
No, I haven't heard about the airplane stuff, but yeah, I mean, things get weird at that, you know, quantum mechanics comes into play. All right, so looking at our temperature scale, so we have absolute 0, and so kind of the nice thing, though, about Kelvin is that it scales linearly with Celsius, so that means, right, every degree difference in Celsius is a degree difference in Kelvin. You can see that reflected from your difference from water freezing to water boiling, so 100-degree difference. And so that means our formula, so our temperature Kelvin can be derived from our temperature Celsius plus 270 degrees, and I'll put that 273.15. So this goes back to accuracy already, and I think there's a question in your homework where it says something of like, it uses the term exactly. And so when it uses the term exactly, what it was trying to go for, and you can look at the homework answers or we could talk later, but it's using this 0.15 when it's saying exact. But, you know, usually when you measure temperatures, especially like in lab, it's pretty inaccurate. So maybe you'll get like, you know, 21 degrees Celsius or something. So usually I don't put decimals after temperatures, so that's why I kind of abbreviate it to 273. But I just wanted to point out that that's what the homework was going for when it uses the term exact, is that it's looking for a higher level of accuracy. That being said, on a test, I'm not going to be that picky about using the 0.15 or not. But, yeah.
You're going to go into like margins of error in this class? Is that more statistics?
Yeah, I mean, that's probably more like analytical chemistry, too, of like error propagation. So again, we're going to do a little bit of that, but only so much.
The 273.15, is that, just to clarify, because I see two different 273s, that's for the conversion factor for Celsius, or is that for water freezes?
They're the same, sorry, same formula, it's just this is more accurate. It's just, in reality, you probably don't need to use the 0.15, but you know, someone's going to say 273.15 somewhere and like be accurate. And so, of course, you're familiar with the Fahrenheit scale. And ironically, I can totally tell you like what temperature all the solvents boil at in Celsius, but I have no idea what that translates to Fahrenheit, and I have no idea what a like normal temperature is in Celsius. So I don't know what that says. But obviously, right, it's a little funky, and we have water freezing is defined at 32 degrees Fahrenheit. Then it's a 180-degree difference between water freezing, water boiling, so obviously it doesn't scale the same. And we have 212, so kind of a little bit of a mess. But with that, you have your formula here. So I would probably write that down, and a good place to put that is your periodic table. So I would, you know, you can write handy dandy formulas on there to help you. Oh. Yep, they are live updating as we speak. So I'll just give people a second to take it in. So again, pretty self-explanatory. If I need to go into more detail, again, please let me know. I can move fast, and that is the one complaint people will say about me is I move fast through the math, but that's only because I'm overexcited. But so right, pretty simple. If we want to convert from Celsius to Fahrenheit, obviously we plug in our temperature in Celsius. And then, right, please excuse my dear Aunt Sally. So multiplication first, obviously, then addition. And then same thing now going from Fahrenheit to Celsius. Notice the parentheses, so obviously do the subtraction first before multiplying by 5/9. And so you might also see 1.8. Oh. So let's see, so 9 divided by 5 is 1.8. So you might, again, see formulas where it's 1.8 times the temperature degrees Celsius plus 32. Same thing. That's all I'm saying there.
Is that like an established rule between the 2 degrees, or is that just an estimation?
I mean, this is pretty much an established rule. Yeah, I mean, it's a conversion factor. Yeah. All right. And so the other little property that we'll talk about is density. So density is pretty important. And so, of course, density is just defined as any ratio of mass to volume. And so, right, that could be grams per milliliter, kilograms per liter, pounds per gallon, right, et cetera, et cetera, et cetera. We could go on and on. So density is also important since obviously, right, it's inherent property or, well, actually, let's go down there. So we have these definitions. So we have an intensive property versus an extensive property. And so I was just saying that density is an intensive property. So what does that mean? Intensive property. And why would I be talking about it being useful for identifying or something? Or maybe other examples of intensive properties. Yeah. Instead of temperature, probably what we want to talk about would be melting point, boiling. Oh, let me rewrite that. No one knows what the heck that is. Melting point, boiling point. And so I'll define it for you guys. So intensive property just means that it's some property that does not depend on the amount. On the amount of substance is what we're trying to say. And so what that means and why I was referring to density, right, is it, I think it could be even one of your labs or maybe one of your lab practicums or something, but you can have, right, an unknown metal and, well, that's one of the first things you can do, right? You can take the mass of it, you can do a displacement with your volume, and then you can figure out your density. So that's, a good basic property just to try to determine what something is. So you have your density, and then so now we can list other intensive properties. So that's where we go back to melting point. So again, it doesn't matter, right, how much of our substance we have, whether we have 1 gram or 1 milligram, it's still going to melt at that same point. It's going to boil at that same point. So what else could be intensive properties? How else do you describe substances? Or
Color.
So color.
About like pH.
pH, that's a good one. Yeah, so every molecule has some sort of pH associated with it, or pKa. Oh. What might be other intensive properties?
The texture.
So texture.
Like crystal structure.
Oh, that's an advanced one. So crystal structure packing. I'll kind of add to this like hardness, you know, like rock hardness, of course. And I'll state of matter, or also write reactivity. So we know, right, sodium metal is going to react with water, whether it's a tiny amount or a large amount. It's going to be a bigger kaboomy.
Like a triple point?
Yeah, triple point would be of a substance. And so any other things, so solubleness. So I was saying a specific heat, solubility, that's a good one. You could also put like immiscibility with that. I can't spell. Like whether it's miscible in a substance, so does it dissolve in water? Does it dissolve in organics? Like you could describe that. Some substances dissolve in both. Some can't go into organics. Some go into water, vice versa. That's a pretty good list. I think y'all did a great job. So yeah, intensive properties. And so while we're here, slowly running out of time, we'll define extensive properties. So this does depend on the amount. And so then, right, it's going to be something that is quantifying that amount. So of course, if you have an amount of something, well, you probably want to get, right, the mass. And again, go size, so length, width, height. So just, again, something that's describing how much is there. Yeah, so weight and mass, pretty similar. And so really quickly, again, running out of time, but we can at least do this problem. Set up our triangle trick in case people haven't seen that. I always like that. So we have density, mass on top, volume. And then have you guys seen this triangle trick? Where you just cover whichever one you're looking for. So let's do this example. So we have, 73.2 milliliters of a liquid has a mass of 61.5. What's its density? So triangle trick, we can cover our density. So that tells us what we need to do. So mass over volume. Yes, that is also back to the definition, but that still helps. Then we can plug it in, 73.2. Oh, sorry, other way. Mass divided by volume, 61.5 divided by 73.2. So that gives us a density. And so, right, sig figs come into play, like we were saying. So we can't just write a random number, right? Calculator spits this out. We don't just go on and on. We look at our problem. 3 sig figs here. 3 sig figs here. And we'll have to do some more mathematical operations with this. But basically, multiplication, division, we retain the number of sig figs that the smallest, least accurate one has. So 3 sig figs, so 0.840. And then use your units, so write grams per milliliter. Okay, in the last 2 minutes of class, see if you can do this last one. So it says determine the volume of an object that has a mass of 455.6 grams and a density of 19.3. So that means we're covering the volume there. So mass divided by density. All right, do we have an answer A, B, C, D, E? I know we're kind of running out of time. I would relook at that. And centimeters cubed is 1 milliliter, sorry. A, B, C, D, E, D, and so I'll punch it in really quickly. So that's why I like the triangle trick. So we can do 455.6 divided by 19.3, and we get our answer. So Thursday we'll do more math. We'll probably revisit this, kind of look at this again with dimensional analysis and unit canceling so we don't feel as rushed. And then we'll work on our metric conversions. So I would probably go home and fill this out so you're kind of ready, and I'll post a copy to the notes later. And then I will see my Tuesday people today at 1:30, so I will run up there as soon as I can. And I will stop this stream.